As I see it, North Atlantic right whales are one of the most iconic and fascinating species of the Atlantic Ocean. But they are facing extinction, and as you know, they have to deal with multiple stresses, which I'd like to focus on in my following presentation. Hello and welcome. I'm Jasmin Hütt from the University of Kiel, and in last spring I did my undergraduate thesis in the lab of Michael Moore at Woods Hole Oceanographic Institution. Together with Peter Corcoran and Julie van der Hoop, we worked on the impact of especially sublevel stresses on the energy budgets of female right whales. Why did we do this? Right whales are in a very severe situation. They are critically endangered and the population has been declining in the last decade. So to achieve the best possible conservation outcome, it is very important to understand why these numbers have been declining and how stresses correlate to the trend. Next to vessel strikes, there are two main threats to right whales that have even been quantified in the past. First, increasing water temperatures in their main feeding habitat, the Gulf of Maine, have caused a decreasing food availability. And second, at least 3/4 of the whole population have been entangled in fishing gear at least once. These entanglement events can last for several years and are very costly from an energetic point of view. Both malnutrition and entanglement can impact the energetics of right whales. Sublevel stresses are known to cause a decline of individual health, a decline of reproductive success, and finally a decline of population health overall. So they can inhibit the recovery of a species. For example, as you can see here, North Atlantic right whales already show a far poorer body condition in comparison to other right whale species. In our study, we focused on three main research questions. First, we wanted to quantify the effect of both stresses on the energy budget of female right whales. Second, we wanted to find out which stressor is kind of worse. And third, we wanted to connect the quantification with the individual reproductive success. We focus on females because they have the highest energetic needs of all demographic groups and they are most vulnerable to energetic stress. So what we mainly did is set up a bioenergetic model based on the historical calving interval of 3 years. 1 year of pregnancy is followed by 1 year of lactation and 1 year of resting. After these 3 years, right whales would reach energetic equilibrium. The model is based on literature values and especially morphological data, which we used to create a generic female right whale. She would be sexually mature and about 13 meters long. What we then did is comparing the energetic income through food with energetic expenses like basal metabolic rate, migration, foraging, pregnancy, and lactation. We then assumed if right whales wouldn't be able to reach energetic equilibrium after these 3 years because of the occurrence of stresses, the resting time might be elongated. And like I said before, North Atlantic show far poorer body condition, so we also applied southern right whale data to the North Atlantic's model, but that's another story. So here I'll focus on the results for the North Atlantics. After we got the energy budget, we then calculated different energy balances for several model scenarios by just subtracting the energetic expenses from the energetic income. Here you can see the natural scenario, assuming right whales would feed on an average plankton density and would not experience any stresses. You can see the income versus the expenses and the energy balance as a black dot. According to the model assumptions, right whales would show a negative energy balance after a calving interval of 3 years. As a consequence, the assumed average of plankton density is too low, and right whales must feed on higher plankton densities than what has been suggested in the literature so far. For example, this could be due to the challenge of measuring plankton densities in the path of a feeding whale. We found both stresses to impact the energy balance of female right whales. Food availability, represented by plankton density, shows a positive or a negative effect. Our assumed feeding threshold is 1,000 individuals per cubic meter, and the mentioned average is 6,600 individuals per cubic meter. A model enabled us to calculate the plankton density necessary for right whales to feed on to reach a neutral energy balance after a natural calving interval of 3 years. And this one is almost 9,000 individuals per cubic meter. In comparison, entanglement in fishing gear only shows a negative effect. Our two main variables here were duration of entanglement for different scenarios of severity. To be able to compare different model scenarios, we calculated energetic loss or gain in comparison to a scenario with a neutral energy balance. Here, I'd like to show you the two worst case scenarios. Assuming right whales would feed on the feeding threshold over the whole calving interval, they would experience an energetic loss of 89%. In comparison, the worst case entanglement scenario leads to additional energetic expenses of up to 55%, on average 15%. So the effect of feeding on the feeding threshold is more negative than the effect of maximal grade and duration of entanglement. Also, already few changes in the wide range of the assumed plankton density shows a very strong impact on the energy balance. Overall, the effect of food availability is stronger than the effect of entanglement in fishing gear. Unfortunately, it is not known below which threshold inhibition of reproduction or even death would occur. So we were only able to calculate additional time right whales would need to reach energetic equilibrium. Please note that each stressor summed together mathematically. Remember, the historical calving interval is 3 years, while in nature, calving intervals of more than 7 years, with a peak of even 10.2 years in 2017 have been observed. Here you can see food availability, entanglement, and a combination of both. One stressor alone almost or does not reach as high values, while the combination of both stresses can reach calving intervals of up to 12.7 years. Overall, the model suggests a combination of multiple stresses to be responsible for the elongated calving intervals we observe in nature. But please also note that because we do not know this threshold, it can be that right whales would die within some of the model scenarios before they reach a complete calving interval. If you think back to the research questions now, we are able to answer them all. And my take-home message for you is that also sublethal stresses can impact the energetics of marine mammals, such as right whales. So as a consequence, there's an urgent need to mitigate these effects by including these findings in appropriate conservation efforts. I'm happy to answer any questions you might have during the conference or via email. So thank you very much and see you soon.